Hello everyone, today I'll be walking you through my VR Fruit Ninja Fit project built for MetaQuest 2 using Unity. This is a complete virtual reality game where players use hand-tracked controllers to slice flying fruits. I'll show you everything from initial setup to the final working game, including all the XR packages we installed, how we configured the project for VR, and every component and script used in the hierarchy. Let's get started. First, let's talk about the project creation. I'm using Unity version 2022.3.41 F1 LTS, which is the long-term support version recommended for VR development. This is our project, MU Fruit Ninja FIT. When creating this project, I selected the 3D URP template. URP stands for Universal Render Pipeline, which is essential for VR development because it's optimized for mobile hardware like the Quest 2 Snapdragon XR2 processor. So our project is already opened and loaded. Now let's start about how we installed XR packages. The first crucial step in VR development is installing the required XR packages. Let me show you the package manager. Uh, so these are all the packages that we used. Let me filter to show Unity registry packages. Yeah. So so here are the key functional packages we installed for VR functionality. This is the XR Interaction Toolkit, version 2.6.3. This is the Unity's official cross-platform VR framework. It provides the foundation for hand tracking, controller input, grab interaction, and teleportation. To install this, I simply clicked install. It's already installed. In the bottom right corner, this package is crucial because it gives us components like X-ray, XR Rain interactor for pointing at objects, XR Direct interactor for grabbing, and the XR Origin, which is our VR camera rig. Next is XR Plugin Management, version 4.5.0. This manages which VR platforms our project supports. It's like a hub that loads the correct VR SDK at runtime. We install this the same way through the package manager. Uh, the third critical package is XR plugin for Oculus version 4.2.0. This is Unity's official support for MetaQuest devices. It provides Quest specific APIs, Android build support, and performance optimizations for Quest hardware. Uh, Now let me show you the Meta XR SDK packages. These are from Meta, not from Unity. Uh, yeah, this is the one. Here is the Meta XR all-in-one SDK version 71.0.0. This is the complete MetaQuest development suite. To install this, I had to first add Meta's package registry. Let me show you how. In the project settings under package manager, I added meta scope registry. The name is meta SDK, meta XR SDK. The URL is packages.unity.com, and the scope is com.meta.xr. After adding this, a meta packages appeared in package manager. Yeah. So next, you could do this now, and the Meta XR SDK includes several sub-packages like Meta XR Core for foundational features, Meta XR Interaction for hand tracking, yeah, and the audio trigger component for we use for the audio we use Meta XR haptics for controller vibration, and Meta XR simulator for which lets us test VR in the Unity editor without wearing a headset. But it wasn't so accurate, but we used it as much as we can. Now about the XR plugin management configuration. Here is the XR plugin management. This is where we enable our VR platforms. One second. Yeah, this is where we enable our VR platforms. This is the Android icon for our MetaQuest. Since Quest 2 runs on Android, I'm clicking the Android platform tab. It's already here. This is the Oculus checkbox which has to be checked in. I've enabled Oculus. This checkbox tells Unity to use the Oculus XR plugin when building for Android. Without this, VR won't work on the Quest. Under Oculus settings, we have important performance options. Stereo rendering mode is set to multi-view, which is the fastest rendering method for Quest. I have enabled fixed foveated rendering, which reduces rendering quality at the edges of vision for better performance. Then this is crucial for maintaining 72 FPS, which is the MetaQuest 2's FPS. And dynamic resolution is enabled to automatically adjust the resolution if frame rate drops. Yeah. Now let me show you how we switch the platform to Android, which is essential for Quest deployment. You have to select in build settings. You can see Android is highlighted in blue, which meaning it's our active platform. Originally, Unity projects default to Windows, Mac and Linux standalone. Then to switch, I selected Android from this list, then clicked switch platform, which is available over here instead of build and run. This process took about 10 minutes as Unity re-imported all assets for Android. Let me show you the Android specific settings by clicking player settings. Yeah. Under player settings for Android, I configured several critical settings. The company name and product name to identify our app. Most importantly, the minimum API level is set to Android 10. Android 10, that is API level 29, which is minimum required for Quest 2. The scripting backend is IL2 CPP, not Mono, because Quest requires ARM64 architecture and target architecture shows ARM64 is checked. minimum of Android 10, API level 29 is recommended, but anything higher is also fine. So quality settings are critical for VR performance. Quest 2 has mobile hardware, so we need to optimize carefully. I've set the default quality level to performant. Here you can see the VSync count is 0. This is crucial. This is crucial because VSync limits frame rates to your monitor's refresh rate, but Quest needs its own 72 FPS independent of the editor. Anti-aliasing is disabled, and but here handled by the VR system. And shadows are disabled because they are very expensive on mobile GPUs. Yeah. The custom render pipeline is set to our URP asset, which I'll show you next. Under graphic settings, the scriptable render pipeline settings points to our URP render asset. This is what makes our project use the optimized universal render pipeline instead of the built-in renderer. Now let me show you the project structure. This is the project window showing all our assets. Here's our assets folder. Let me go through each important folder. The prefabs folder contains all our reusable game objects. I'll show you these in detail shortly. The scripts contains all our C# code, 5 main scripts that drive the game logic. Sound has our audio files like the cam shots, like the fruit spawner sounds, sword slices, and fruit splash sounds. And materials contain the visual properties for our 3D objects. And scenes as our game levels. The main scene is called the VR Fruit Ninja. Let me explain how we got these prefabs and what they are. A prefab is a reusable template for game objects. These are our fruit prefabs. We have 11 types: apple, banana, watermelon, strawberry, lemon, peach, pear, cherry, avocado, peanut, and tomato. I downloaded these 3D models from the Sketchfab. You can also do it from the Unity Asset Store. I'll guide you how to do it from the Unity Asset Store. You can directly go to the assetstore.unity.com, which is a website available, and download it. After downloading the free poly fruits from any website, you can use the Unity or Sketchfab, and found a package with these models. After clicking add to my assets, I open the package manager in Unity. Change the drop down to my assets. Found the fruit package. Not here. Yeah, if you do it with the Unity Asset Store, you'll get it out here. I used the Sketchfab and directly dragged it and added it to my assets. So this bomb prefab uses a simple sphere with a dark material. Let me show you the inspector. Yeah, the dark material. When you hit a bomb, it resets your score to 0. That's the penalty mechanic. This is the fruit spawner prefab. It's a cannon. It has a mesh that looks like a cannon. I mean, we tried, but it's a transparent one for ours, and contains this fruit spawner behavior. This is the script that shoots fruits at random intervals. This is the katana prefab, that is our sword. This is what the player controls with their VR controller. It has a collider. Yeah, it's a part, so it has a collider to detect hits and the saber hit behavior, which is in the blade part, will detect hits, and then the saber hit behavior script uses it. Now let's examine the scene hierarchy. This shows every object in our game world. I'll go through each one from top to bottom. First is the XR. This is the XR camera origin. The inside XR origin. So let us see the interaction ring OVR hybrid to show the child objects. Let me show you what's inside. You will be seeing the OVR camera rig, which contains the tracking cameras, one for each eye, and to create the stereoscopic 3D effect. It also has the controller anchors for left and right hands. These anchors track the physical position and rotation of your Meta Quest 2 controllers in real time. When you move your head in real life, these anchors move in the exact same way in the game. Now, about our katana. This is the virtual sword that the player uses to slice fruits. This object is parented to, and it follows the the controller anchor. So when you swing your Quest controller, the sword swings with it when you hold and grab it. Let me show you the inspector. First, let me explain each component attached to the katana. First is the transform component. Transform component, which shows the sword's position in 3D space with the X, Y, Z and coordinates, its rotation in degrees, and its scale. The position is set relative to the controller, so it appears in front of your hand at the right angle. This is the mesh renderer, and this is we have the mesh filter component below, that is the mesh render, which actually displays the model on screen using the assigned material. You can see it's using a metallic material to make the blade look shiny and realistic. You have the option to change it here. We just changed it. Now we have the collider component. This box collider is critical. This invisible box surrounds the sword blade and defines its physical boundaries. When this collider touches a fruit's collider, Unity triggers a collision event. I sized this collider to match the blade shape, so collision detection feels accurate. Here's our custom Saberhead behavior script. This is the C sharp code that we wrote to detect when the SWOT collides. Uh, so when the SWOT collides with fruits or bombs. Uh, it has a reference to an audio trigger component, which I'll explain in a moment. This is the audio trigger component. The audio trigger component is from the Oculus Interaction SDK. Unlike Unity's standard audio source, this provides 3D spatial audio optimized specifically for VR. The audio clip is set to samurai slash. Yeah, audio clip is set samurai slash. The swoosh sound when you hit something, because it's spatial audio. The sound comes from the 3D position of the sword, creating realistic audio feedback. Volume is set to 1. Is set to 0.3, and these 3D sound settings determine how the audio fades with distance. Now let's look at the fruit spawners. We have 3 of them: fruit spawner left, right, and the center one. These are the cannons that shoot fruits at the player. The transform shows the spawner's position. The left spawner is positioned to the player's left side, and its rotation is angled to shoot fruits towards the center of the player area. Each spawner is rotated differently, so fruits come from different multiple directions, making the gameplay more challenging. This is the fruit spawner behavior script, which is the most important component. Let me explain this. The spawn interval is set to 3. This is the initial time in seconds before the first fruit spawns. The prefabs array is the list of all possible fruits this cannon can shoot along with the bomb. Yeah, this is the. You can see I've dragged in all the fruit elements into this. The apple, watermelon, strawberry, pear, peanut, peach, peanut. There's a clone of peanut. Yeah, cherries and bomb. The script randomly picks one of these each time it spawns. Shot strength is set to determine how fast and far fruits fly. I have it to 6.2. And there is an audio trigger component too, which plays the cannon explosion sound when fruits launch. This is a fruit prefab. Let me show you what's inside a fruit prefab. I'll select this is apple. So all fruits have same component structure. Each fruit has several critical components working together. First is this transform for position, rotation, and scale. Fruits are scaled to realistic sizes, about 0.1 to 0.2 meters. The mesh filter contains the 3D apple model, and the mesh renderer displays it with the red apple material. The rigid body which we used is here. It's absolutely essential. This makes the fruit obey physics laws. Mass is set to 1, which determines how heavy it feels. Use gravity is checked, so the fruit falls down after being shot, creating realistic parabolic arcs. Drag is the air resistance. I set this slow so fruits fly smoothly. And critically, collision detection is set to continuous, not discrete. This prevents the sword from passing through fruits when swinging fast, which is a common problem called tunneling. Each fruit has a collider, either a sphere collider or for round fruits, or mesh collider for irregular shapes, or this capsule collider. This defines the fruit's physical boundary for collision detection with this sword. This is the fruit/behavior script. The fruit/behavior script handles the visual effects when you slice the fruit. It has references to the particle system for the juice splash, the mesh renderer, to hide the fruit model after being hit and is tagged as fruit. So the SWORD script knows how to handle it. Inside each fruit, there are child objects. One contains the particle system component. This creates the colorful juice juice explosion when you slice. The particle color matches the fruit. Red for apples, yellow for lemons. I used start color yellow for all, so it looks good. Green for watermelon juice. Another child object has the audio trigger. You can have the audio trigger script which plays for the squish sound, which plays from the fruit's position in 3D space. Now regarding the bomb prefab has the exact same component structure as fruits: rigid body, collider, fruit splash behavior, and particle effects. The only difference is it's tagged here. The fruit is tagged as fruit. The bomb is tagged as a bomb instead of fruit. When the SWORD script detects a collision with the bomb tag, it calls Core Manager to reset the score to 0 as a penalty. Now the game manager. Moving to the game management. The game manager's object is an empty game object that acts as a container for our manager scripts. Inside we have the game controller script and the score manager script. They use a singleton pattern. That means there's only one instance of the entire game. We thought of making it scoreable, but it was glitching, so we had to remove the score manager and the game manager. Usually the game controller script manages the game state machine. It has references to the start menu and the game over menu UI objects which is there. It also references all three spawner objects in the spawners array. The script provides public method start game, which hides menus and activates all spawners, and game over, which does the opposite, stops spawners and shows the game over screen. These methods are called by UI buttons. The score manager script is simpler. It has an integer variable for the current score starting at 0 and a reference to the score text UI element. Yeah, as you see here, I had to delete it, but I still didn't, so I'm just explaining it to you. It provides add point to increment the score, reset score to set it to 0 when you hit a bomb, and update text to refresh the displayed score. Currently, add point needs to be called when fruits are destroyed. That's something to wire up if it's not already. Next is the canvas, which holds all our user interface elements. In VR, this needs a spatial setup. So you have to select the render mode to world space so that it renders as a this is crucial for VR because screen space UI would be flat against your face, which is disorienting. World space means the UI exists as a 3D object in the game world that you look at from a distance like a floating screen. Inside the Canva, I have several UI items which had to be exist, but we have only one now because we have been trying to solve the glitch we have faced, and in the process we have deleted the game manager and score manager and just kept the main mechanism. So here is score text that displays the current score. It's using TextMesh Pro, which is Unity's advanced text system with better quality than the legacy text component. The text is large and positioned where it's easily visible in VR without requiring the player to turn their head too much. The font size needs to be quite large for VR readability. Yeah. The directional light simulates sunlight coming from a specific angle. This illuminates all objects in the scene. The light component has settings for color. I kept it white and intensity. The mode is real time, but for better VR performance, I could bake this lighting into textures. The rotation of this object determines the sun angle and where shadows fall. The dojo mockup is our environment asset, the Japanese training hall background. This is purely visual to create atmosphere and immersion in VR. It has a mesh filter with the dojo 3D model and a mesh render with materials for the wooden floor and walls. No physics or scripting required, it's just scenery. This object contains our background music, the shamisen dance track. It's traditional Japanese string music that fits the Fruit Ninja theme. This would have an audio source component with the music clip set to play on awake and loop enabled so the music plays continuously. The volume is set lower so the sound effects lower than sound effects so it doesn't overplay gameplay audio. That covers every major object in our scene hierarchy. To summarize, the interaction with OVR hybrid provides VR tracking. The katana with collision detection is attached to the right controller. 3 fruit spawners shoot physics-based fruits with random intervals. Each fruit has rigid body, physics and collision detection. The game managers handle game state and scoring. The canvas provides VR optimized UI. The event system processes input and the environment objects create the visual setting. Everything works together to create a complete VR experience. Yeah, so next. So now we'll have a script walkthrough. Let me explain each script in detail. We have 5 core scripts that make the game work. Make the game work. First is the fruit spawner behavior. Let me walk through this code. At the top we import Unity engines and Oculus interaction namespaces. We declare public variables for spawn interval, the array of fruit prefabs, short stint and a private audio trigger for the cannon sound. In the start method we initialize the timer and get the audio trigger component. The update method runs every frame. It increments a timer using time delta time, which ensures frame rate independence. When the timer exceeds the random interval between 2 and 10 seconds, it calls spawn fruit and resets the timer with a new random interval. The spawn fruit method plays the cannon sound, instantiates a random fruit from the prefabs array, gets its rigid body component, applies a forward force using add force with force mode impulse for an instant cannon shot effect, and adds torque with random values to make the fruit spin. Finally, destroy is called after 10 seconds to prevent fruit buildup if they are not hit. Now next is saber hit behavior. Attached to the sword, the script uses on collision enter, which Unity automatically calls when the sword collides with something. We check the collision object's tag. If it's tagged fruit, we play the slice sound, call the fruit slice method to trigger effects, and destroy the fruit after 0.2 seconds to let the particle effect play. If the tag is firm, we do the same, but also call score manager.instance.reset score to reset the score to 0 as a penalty. Next is the fruit slash behavior. It's attached to our each fruit prefab. It has references to the particle system, mesh render, and audio trigger, and a boolean flag to prevent playing effects twice. The slice method is public, so saber hit behavior can call it. When called, it plays the splash sound, starts the particle system, and hides the mesh by setting mesh render dot enable to false. Yeah, to false, and sets the flag to true, so it only happens once. Now the game controller. Game controller uses the singleton pattern with a static instance variable. In Awake, we set instance equals this. The start method shows the start menu and hides game over menu and deactivates all spawner. Start game is called by the UI button. It resets the score, hides menus, and activates all spawners by looping through the spawners array. Game over, game over does the opposite. It deactivates spawners and shows the game over menu. Set spawners active is a helper method that calls set active on each spawner game object. Now the score manager, also singleton. It has a public integer score starting at 0 and a reference to the text mesh pro UGUI component. Awake sets the instance and calls update text. Add point increases the score and updates the UI. Reset score sets score to 0 and updates the UI. Update text simply sets the text component to display score colon plus the current score value. Next is the sounds. Let me explain our audio system. We have 5 audio files. Air explosion for the cannon shot. The samurai slash for the sword hitting. The tomato squish for the fruit splash. The sabra, the saber humming for ambient sword sound, and shamisen dance sound, shamisen sword sound dance, which is Japanese theme background music. These are all MP3 format for small file size. Instead of Unity standard audio source component, we use audio trigger. We use audio trigger script. It has a clip in inspector. You can see the audio trigger has a clip reference, volume in and max distance for 3D fall off, and spatial blend set to 1 for full 3D positioning. When we call audio trigger dot play audio in the code, the sound plays from that object's 3D position, so you can actually hear where fruits are spawning based on sound direction and distance. Building for Quest 2. To deploy this to Quest 2, we build an APK file. In build settings, Android is selected, and I've added the VR fruiting as scene to scenes in build by clicking add open scenes. Clicking build generates an APK file. This takes several minutes as Unity compiles C# to C++, compresses assets, and packages everything for Android. To install on Quest 2, I connect the headset via a Type-C to Type-C cable with developer mode enabled. I used adb command, adb install app.apk, or drag the apk2 into SideQuest software. Alternatively, build and run does this automatically. So I use build and run, and it automatically installs in my Quest. Once installed, I can put on the Quest 2, launch the app from unknown sources, and play the game by physically swinging my controller to slice fruits. During development, I tried testing using the MetaXR simulator. Pressing play in Unity lets me test VR without using the headset. But as we had a headset, we always use the headset to even more accurately know the glitches. It's not using the XR simulator, it's not as accurate as real VR testing, so we use the VR as we had access to the console. The console window shows errors and debug messages. When I had issues with missing prefabs errors, earlier errors appeared here. I fixed them by copying the correct prefab files from a backup. For performance monitoring, the profiler shows CPU, GPU, and the memory usage. VR requires consistent 72 FPS on Quest 2 to prevent motion sickness. I optimized by using URP, disabling shadows, keeping polycounts low on fruits, using continuous collision detection, destroying fruits after 10 seconds, and enabling fixed foveated rendering on Quest settings, which reduces rendering at the edges where you don't look directly. So, to summarize, this VR Fruit Ninja project required installing XR Interaction Toolkit, XR Plugin Management, XR Plugin Oculus, and Meta XR SDK version 71. We switched the platform to Android, configured Quest specific settings in XR Plugin Management, downloaded fruit models from the asset store, built our scene hierarchy with XR origin for VR tracking, spawners with physics-based launching, fruits with rigid body and collision detection, and a sword with collision detection and spatial audio, UI elements for score and menus, and 5 C# scripts managing spawning, collisions, effects, and game state and scoring. The audio trigger component from Oculus Interaction provides 3D spatial audio. We optimized for Quest 2's mobile GPU using URP and performance settings. The result is a fully functional VR game that tracks hand movements, launches physics-based fruits, detects collisions, provides audio, visual feedback, and maintains 72 FPS for a smooth, immersive experience. Thank you for watching.